My talk is on the batch process automation. I would like to combine to the, maybe I should later point, sorry. Use my research work have been long time. They illustrate this on injection molding example. And my talk would first give an introduction of what injection molding process is, then generalize what the characteristic of batch process has. Then we talk about batch automation, specifically on the following 4 areas, but due to time, I would mainly focus on the control. I skip the quality measurement. Then toward the end, I talk about plant-wise, combine multiple lines of batch process together. It would be ready for big data and machine learning for industrial application. Finally, I'm going to conclude. So what injection molding is? Injection molding is a process converting plastics or polymers into various plastic products used in many different sectors like transportations, home appliances, telecommunications, and medical areas. Today, it would be very difficult to imagine without the plastics what sort of life you would have. And the major process of injection molding is done through a machine called the injection molding machine, as shown here. This is the machine in my lab. And the machine have been modified and retrofitted for control system development here. So in the yellowish box here is contain a piece of metal, which is essentially contain the shape of the plastic product you intend to have. And this part of the machine is basically prepare the material so that it could be injected into the mold. The process is like this. Started with mold clothing, then inject of polymer melt into the cavity until the cavity is completely filled. Then the process switch to so-called the packing phase, so that high pressure can be maintained, so that additional material can be packed into the cavity so that you can compensate for the shrinkage related to solidification. The process continues until the part is solidified on the inside the mold. In the machine side, it's prepare plastification so that you can prepare for the next cycles. When the part is sufficiently solidified, the mold open, the plastic parts is taken out, the process repeats itself. So you can see the process including several different stages of the activities. And during different phases, during different stages, different controlled variable will be used to affect final product qualities. For example, in the filling or injection phases, the injection velocity would be dominant variables. During packing stages, the packing pressure would be the dominant variable, such and such. And now let's relate to injection molding to the more general processes. In chemical engineering, we all know that there's 2 types of processes. One is called continuous, the other is called batch. For the continuous process, is theoretically steady state with a quotation. You have a material being continuously fed into the process, product continuously taken out of the process. And large chemical plant like oil refinery, fertilizer plant are such typical continuous processes. For the batch processes, the material goes through ordered set of process activity to form a product or a group of products. And then the process repeats itself to form more of the same products. Here are some typical products of batch processes. Now let me use a cartoon to illustrate the key characteristics of batch process. The batch process goes through several different phases, form one product, and then this process repeats so that more of the same product being manufactured until the sufficient number of products being manufactured. The same process is switched to manufacture another different kind of products. During different phases, the quality variable or process control variable may changes from phases to phases. I use 16 Chinese words here to illustrate the batch process characteristics. Basically, one processes have been used to manufacturing different type of products over its lifetimes. During the manufacturing of same product, the processes are repeated to form of more of the same products. During the manufacturing of one product, the process goes through several different phases. During each of these phases, the relationship or correlations among the variables and the variable you concern may changes, okay? And the English words I cannot summarize into equivalence, but if you use Chinese, you have equivalence of 4 different phrases. In Chinese, we'd like to take the hidden methods. For example, the first word of each sentence or last word of each sentence. If we take the first word of each 4 sentences here, and you result in these 4 characters, this 4 characters basically means multi-time variations. Okay, for process control, we know there are time variations, but then I have created a strange name so-called multi-time variations. And this multi-time variations, it reflects characteristics of batch process very well, because the dynamics or characteristics changes along the time for batch process. It also changes along batch and also changes with product. We can take the batch process as 3 time dimensions of different scale. One is the traditional time, another is batch time, another is the product time. So the batch process characteristics changes with these 3 different time scales. And obviously, when product changes, we need to change the conditions. For example, recipes, operating conditions, and the product specification changes. This in turn results in process characteristic changes, like dynamics itself, the variable you need to be controlled, and finally, what kind of quality you're interested. And those changes further result in the changes of requirement of automation system. For example, the model changes, and then the control strategy may need to change. The monitoring and the analysis strategy may also change in response. The optimization strategy may change in responses. And there's another requirement related to, relate to this. You know, when the project changes, product changes, you cannot start a new product for a year and a half before you produce next product. You need to immediately start to produce a new product. So therefore, the batch processes face 2 challenges. One is large dynamic range adaptation requirement. Then another is you need to have this adaptation done very quickly, rapid adaptation. So I summarize the contradictions or the problems related to batch processes. The batch process earlier I said on this Chinese character says it's multi-time variations, but also the batch process have certain requirement. For example, the operation have to be done timely, the control have to be accurate, the process have to be safe, the product quality need to be optimized, and it's resulting 4 contradiction or problems for the process automations. When product changes, typically the model changes. So it's resulting the complexity of remodeling and time effort taken in remodeling versus the instantaneous model requirement contradictions or challenges. This is the one challenge. In terms of control, you have large operating range versus consistent performance requirement contradiction. In terms of monitoring or analysis, the process have complex phase natures, yet you need to do accurate monitoring and analysis in times. Most importantly, we are manufacturing certain products. Every product have direct quality estimation, for example, dimension, weight, and strength, etc. However, those things cannot be measured online. We only have indirect quality estimation. So this is the 4 contradiction. So the batch process research is based on so-called multi-time variation nature. How do we systematically develop modeling, control, monitoring, and optimization result to result so-called high performance batch automation system? And for high performance batch automation system, we have this 4 block need to be addressed, and the modeling is the foundation, and the control is the main for ensure safety and consistency. Monitoring is for the analysis and safety, and ultimately quality and efficiency is the goal. So therefore, we need to solve this following 4 problems. One is how do we do efficient modeling after product switches? Number 2, how do we develop accurate control with large dynamic operating range? Number 3, how do we do real-time monitoring and analysis to suit this multi-phase nature characteristics? Finally, we have to do quality measurement and multi-quality optimization. The following work are going to illustrate some of the work we have done on these 4 areas. Now let's revisit the different phases of injection molding, and we're going to focus on the injection phase and to illustrate the control of injection velocity use some of the philosophy we developed. And this injection velocity control in my group have done over 2 decades. It's gone through the following 4 or 5 stages. In the early days, we directly sort of applied the continuous process control strategy to the injection velocity control. Then we realized the deficiency. We modified the continuous process control strategy to fix some of the issues. Then we realized that those strategies did not really explore the batch process nature very well. One of the most important nature of batch process is repeats when you're making additional products. So we introduced iterative learning. Finally, we propose a method of our own to suit batch process natures. Let me illustrate the work we have done on this. So we started the work with industrial request to provide feedback control for injection velocity. And for injection velocity is basically the velocity you pushing this screw forward so that you can in turn pushing the polymer melt into the cavity. And before our work, actually, the injection velocity could not be closed loop controlled. It's been done in so-called open loop control. So we take the challenge. We realized that it cannot be done, so that we need to fit some fancy actuator. So we retrofit the machine with state-of-art fast responses servo valve to control the injection velocity. This is the retrofit servo valve, which is quite expensive. It's as expensive as the entire machine. We use that to control the injection velocity. We started with the traditional method of PI control. We intend to have the velocity to follow certain set point profile. You can see with the PI control, certain time, certain velocity, the velocity can be controlled. In other velocity, it's actually machine simply oscillates. This is because of inherent nonlinear and time varying characteristics, which is exceptionally strong. Let me illustrate how strong it is through this material property illustration. It shows the shear rate versus viscosity. And we can imagine the shear rate is directly related to injection velocity. The viscosity is related to how difficult the polymer is flow into the mold cavity. You can notice this the log scale plot. You can see the velocity, the viscosity changes with velocities not over 10%, 20%, over tens of thousands of percent. This is one thing. The another thing you can see, the viscosity also change very significantly with melt temperature as well. So that indicates the machine is really have a very, very strong nonlinearity. So to address that, about 15, 20 years ago, we introduced the self-tuning adaptive control to the injection molding process. It's I don't think we need to explain the adaptive control to this community. So I go through this slide, skip. So with a very large forgetting factor, typically adaptive control, the textbook suggests the forgetting factor should be 9.9, 9.5. What we use here, forgetting factor is 0.7. With that strong forgetting factor, we being able to control the velocity well with different levels, as you can see here. And our collaborator was very happy because this is for the first time injection velocity could be closed loop controlled. And then what we do, we zoom up, we zoom in this region. You can see the velocity can be changed from one level to another, taking about 20 control samples. In this particular case, about 0.1 second, what was very fast at that time. Then we were not happy. We realized for batch process, actually the start point profile is fed to the machine before the process starts. You can take advantage of that so that we can introduce a sort of feed forward to the adaptive control. And here's the result of feed forward control result in green lines. You can see the combination of feed forward and feedback dramatically improves the response speed as shown here, as shown in the zoom in plot. The original feedback control take about 20 control periods. And with the feed forward, we only take about 6 steps. We can control the velocity from one level to another. That's reaching the limit of the valve. Then we also realize there's a process delay associated with this. We can also cheat the machine by shift the profile of injection velocity forward by the number of delay steps. If we do that, you can see the process can switch from one velocity to another velocity in 4 steps or 20 milliseconds. That's kind of work at that time is not seen before. And then with adaptive control, you need to have start with an initial model. The model then it's being updated, the control performance can improve with time. And we can also introduce sort of cycle to cycle or batch to batch learning. We can update the initial model from the end of the last batches dynamics. If we do that, and then the control performance for early stage of the phases can also improve dramatically. Now let me summarize what we have done. We have introduced adaptive control. In addition to that, we added feed forward, profile shift, and cycle to cycle learning. With that, we can control the injection velocity very tightly under different conditions. We were very happy, the industrialist was very happy. Then we approached by another industrialist, say, okay, your injection velocity control, your injection control is very accurate, but using this very expensive valve make the real industrial application not feasible. So can you do accurate control with a regular cheap valve, a proportional valve? So now this is the proportional valve. The price of the proportional valve and the servo valve is about 50 times different. So we took the challenge and then we thought about of our early work. Actually, our early work to improve the performance, we really need to take the batch to batch learnings. So the systematic way of batch to batch learning is obviously the iterative learning control. Again, I do not need to explain what is the iterative learning control for this community. Then the question is, okay, if we combine feedback control together with iterative learning control, how can we improve the performance along both time and the batches? This is the one thing. Then how do we design these two controllers simultaneously optimal? This is the another thing. Took that, we developed so-called 2-time dimensional model predictive control combined with iterative learning control. And for that, we developed the 2D MPC in this way for a single batch. For the future batches, we can also do 2D MPC through this kind of prediction model. Correspondingly, we could have single batch 2D MPC cost function designed that in this way, or multi-batch MPC cost function design in this way. By optimize this cost function, we can result our updating control law, RK. And the control law RK optimized, resulting in this interesting structure, and contains the following 3 elements. One is the last cycle's control error over the future prediction horizon, and the current control cycles of past information and the current cycles past information. We can naturally break this controller into iterative learning control and MPC control. Information-wise, we can illustrate as shown here. This is the traditional time. This is the batch. At the current batch, current time, batch K time T, we can use the past information of the current cycle. Together, we can use the information of past batch future time. So in other words, we sort of can predict in the future by taking the repeatability of the batch process. With that, we developed our control law and using the slow proportional valve to control the velocity. As you can see, with the first cycle, we have nothing to learn. The control performance is very poor. With the future cycles, the performance improves. And let's say here you can see cycle 11, we almost have perfect control despite of this very slow valve. If we zoom in the velocity responses around the step changes, you can see the velocity control is being followed very tightly. And then the question is, okay, if we can control the process variable very well, can this really result in the product quality improvement? This is the product weight variations over 1 day production. You can see there's some variation after the process switching to after the process into the steady state. You can see the weight variation here is about 0.12 grams. For the same machine, if we're using our control strategy, you can see the same weight variations. With this 2D control, the weight being controlled very precisely. Okay, in this particular cases, the weight variation have reduced 3 times to 0.04 gram. We need to point out the balance we're going to measure the weight. The resolution is 0.01 gram. If we use a better balance, maybe the tightness of the weight repeatability would be even better. That's the work related to the control. And for the batch process, when we make one product repeatedly, during the process, we accumulate lots of data. With this lots of data, we can develop a good model. That's no problem. But then the question is, when the production of this product is over, we switch to new production of a new product. We do not have knowledge. We do not have data. The model you developed here is no longer fit with the new process. The question is, how can we develop new model for the new process or new product quickly? We introduced the idea called the model migration based on this process. We call this original process. This process, new process, they have good similarity. So rather than develop the model from scratch, how can we migrate the original model to a new model with a few data quickly and efficiently? This kind of a modeling philosophy we call the model migration philosophy. With this model migration philosophy, you can develop numerous different model migration techniques. Okay, here I illustrate one most simple, possibly most efficient one to migrate an old model to a new model. Here, the old process, we have an old model. We make use of process similarity, use a little bit data, we migrate to a new model. For example, with the old process, we have lots of data. We can always build a relationship by any data-driven method or any method. With the new model, we can use one most simple one. For example, we can use the import and output scale and the bias shift method. Okay, and with this scale and the bias shift method, the only thing we need to do is to find the scale and the bias coefficient. We can do this through optimization to find this thing here. And this method, it was applied to our process. It's shown to be very efficient. And also people have using this scaled bias shift method applied to other industry, for example, glass industry, iron and steel industry, pharmaceutical industry, and even batteries are found to be very efficient. So this is one of the model migration strategy we proposed. We also have proposed other strategy because of time. So I'm not going to cover that in details. And for the batch process monitoring, we know that the process batch process characteristics resulting in this three-dimensional data matrix. The great work of John McGregor was able to convert this three-dimensional matrix into two-dimensional matrix so that the process monitoring strategy can be efficiently applied. One problem with this, by doing this, the clear phase nature is no longer visible or buried. To understanding that, then we have decided to develop our own batch process monitoring, considering different phases. And with these different phases, we could build the relationship between quality and different phases. That was our early work, possibly again 15 years ago. Then after that, we realized batch process switch from one phase to another does not jump. It have a transitional stage. This transition actually have more impact to quality variation. So we introduce transition phases for the batch process monitoring as well. After that, we learn from the great work of our colleagues, for example, Joe, and we treated each of these phases as the one block of data. And then we can look at the relationship between different blocks, and also we can look at the data, how it varies within the phase, within batch. So within this block data, we can easily analyze the batch process more efficiently. So that's the work we have done in terms of monitoring. Because of time, I'm going to skip the quality measurement. So basically, we have done 4 areas for work. One is the modeling. The modeling, we make use of process similarity so that we can develop model migration strategy. It can allow you to efficiently build the model for different products. With the control, we developed so-called 2-time dimensional model representation. For that, you can deduct 2D identification, 2D state estimation as well. We're going to skip that. With this 2D representation, it's allowed your control to improve around both time direction and batch direction. For the monitoring, we divide the data or process into different phases so that allowed you to do more efficient monitoring and analysis. For the quality, I did not have time to talk about it. We will make use of batch process characteristics by install a sensor at one fixed location. You can monitoring different things over different phases. We call that those single sensor multi-sensing, okay? With that, it allows us to do a multi-quality optimization. And those technology we developed are also being applied to a real-world process of injection molding. We have developed a commercial control system as shown here. And this control system is also like Richard say it's a plug and play. So you just plug this controller to the different machine, and then you can see a significant improvement with the control and the quality consistency. And we also engage into a batch process smart plan effort through our injection molding effort. We try to convert manually intensive operation to fully automated plant here. We also have developed the injection molding manufacturing execution system, allow multi-machine to be monitored and analyzed simultaneously. Here I illustrate a factory with 40 different 40 machines manufacturing products simultaneously. We can monitor and analyze that. With this, we can accumulate data from different production lines. So it's really, with this, we can really to do some real industrial big data and machine learning research. So, sorry, I was overrun 2-3 minutes. So I would like to conclude my talk by make the following statements. One is the polymer processing quality and efficiency can indeed improve significantly by process control or process system engineering work. This is number one point I would like to state. Number two, methods developed for continuous process may not fit well for batch process. Therefore, we need to develop a strategy specifically for batch process. By exploring the corresponding process nature, we can develop a new and more efficient algorithm and methods. And with that, particularly today with the IoT, 5G, and faster internet, we really can connect different devices, different production line together. We should be able to do real big data machine learning work across different lines. So that's all my talk. Thank you very much.